Let us discuss about the first goal, data reduction. If you look at this, the first principal component is capturing 76% of variance, and the second is capturing 13% roughly. And both these principal components put together would capture 89% of information. The third principal component alone is capturing 4.77% of information. The first three principal components are capturing 94.75, roughly 95% of information. Now here is a business decision that we need to take. Do you need 90% of information? If you need 90% of information only, then you have successfully reduced the number of variables from 6 to 2. However, if you want to capture 95% of information, right, then you have successfully reduced the number of variables which were originally 6 to 3. Because if you choose only 3, your job is done. 95% of information is captured. So here is where we need to take a call. Is it okay for me to lose 5% of information? And is it okay for me to get 50% data compression? From 6, I have reduced it to 3. So you're reducing your data set size by 50%. Is this okay for you? Or do you want to lose 10% of information and compress the data by probably 60%? What is better for you? Here is where you need to couple this with your domain knowledge. You need to check with your domain experts and subjectively take a decision on what you want to do. And also, you need to look at the marginal improvement. For example, one PC captures 76.86% of information, the second one 13%, third one 4.77. Now from third principal component to fourth, the amount of variance that is captured is decreasing significantly. Right? So do you want to go further? For marginal improvement, you can look at this in this way. From 94.75% variance captured by the first three, if you add another principal component, only 2.7% more is getting increased variance. So for 2.5% increase in the variance, do you want to include a new principal component altogether? Or does it not make sense? So this is how you need to couple this with your domain expertise, and this is very subjective in nature. So the idea here is choose the first few principal components and drop the rest. Probably you want to choose the first three, 95% of information, that's very good. Or maybe you want to go with the first two because roughly 90% of information is getting captured here also, right? And then you take a call. This is your goal number 1. So how many variables are too many is very subjective in nature. It all depends on the business logic. Sometimes maybe you might have 50 variables and maybe you only have 10 records. 10 multiplied by 50, that is dimension is 500. It doesn't really make sense for me to do a PCA maybe. And say here you have 1000 records and 50 variables. 1000 multiplied by 50 is your dimension. So that would be 50,000. So those are too many values for me. So probably we can apply PC on that, principal component analysis. Under some scenarios, maybe you have 50 variables, but maybe the 10 inputs capture more or less similar kind of information. So maybe I want to apply principal component analysis on these 10 inputs, and probably I want to come up with one single principal component, right, which captures the information captured by all of these 10, because all of these 10 are probably capturing the overlapping information. So I'll use this principal component, plus I will use the rest of the 40 input variables as is. The reason being, the moment you try to do some mathematical transformation and come up with principal components, the explaining power goes away. Right? The explaining power goes away. So maybe if you, for example, when it comes to a linear regression, a negative value here means something for you. If beta 1 value is negative, that means for every unit increase in your SAT score, your output value is reducing. You can infer in that way, but using principal components, that kind of direct interpretation is not possible. So if your goal, ultimate goal is to just do prediction, then principal component works well. But if your goal is to also explain the various input variables, then probably principal component analysis might not come in handy. But still we'll look into a few ways of, naming these principal components to get back your, explanatory power to some extent. But we'll discuss that. So probably this is making sense, right, on what are the widespread applications of your principal component analysis. Okay. It can also be used for data compression, but let us discuss about basics of matrix. 1, 2, and if you take a transpose of that, it's the rows become columns. If you transpose this matrix, this is a squared matrix, row becomes column, the second row becomes the second column. If you transpose this third matrix, this row becomes a column, this row becomes this column, and the third row becomes the third column. So you're just transposing the data. One more thing is matrix multiplication. Whenever you want to multiply two matrices, and if you want to know the dimension basically, so dimension is all about rows multiplied by columns. Here in this matrix A, it's a 3 by 2 matrix. So you have 3 rows and 2 columns. And this matrix B has 2 rows and 4 columns. And if you were to multiply A with B, then remember that the number of columns here and the number of rows here should be the same. For example, if you have A, which is 3 by 2 matrix, and if you try to multiply it with B, which is say 3 by 4, you cannot multiply because the number of rows, columns of matrix A and the number of rows of matrix B are not the same, right? And how do you get the resultant matrix? Remove this 2 and 2. It's a 3 by 4 matrix, the resultant matrix. And one more thing that you need to remember here is that A multiplied by B is not equal to B multiplied by A. So for example, if I reverse the situation here, B will be a 2 by 4 matrix, and if you try to multiply it with A, which is a 3 by 2 matrix, you cannot multiply because these two are not the same. Okay. Now we have identity matrix. This is an identity matrix, right? You have a diagonal and upper triangle and the lower triangle are the same. It's identical basically. So if you multiply two matrices and if you get an identity matrix, then you can represent that in this way. B is equal to A inverse. So if you want to mathematically rightly make statements, then A is left inverse of B. Because A multiplied B is not equal to B multiplied by A. The order is very important. If you get A by B, then A is left inverse of B. It's towards the left side. And B is right inverse of A. B is right inverse of A. Right? This is how, a matrix works. Now I've explained you about that because I want to explain about data compression a little. So you have your principal component scores, which is an n by n matrix. You have your scaled data, and if you multiply your scaled data with principal components, right, you get back your principal component score. So this is something like this. Scaled data is your standardized data or normalized data. And if you multiply these two, right, you can multiply because you have n and n here, and the resultant matrix will be an n by n matrix once again. That's your PC scores, right? That is what I've represented here. So if I go back here and try to explain you all, this, I'm speaking about this part, is an n by n matrix, right? Rows by columns. You have n rows and n basically columns. And this PC scores, how are you getting that? When you multiply your standardized data, this is your standardized data. If you multiply the standardized data with your principal components, you get this. And remember, your principal components is a small data set. Since you have 6 variables, here also you'll have 6 components. So it's an n by n matrix, or it's a 6 by 6 matrix. The same thing is represented here. I have not done anything different. I'm just mathematically trying to represent that. Now if you take this principal components on the other side, it will become inverse. So we have discussed this. A multiplied by B is equal to identity matrix. If that is the case, then B is equal to A inverse. If you take A to the other side, it will become an inverse basically. So it's becoming an inverse here. And here the n by n matrix inverse, that's similar to your transpose basically, right? So what can you do? Rather than choosing all of your input variables, you can probably choose only the first 2 principal components and get the job done. That is the logic behind this. So if you have an image which is worth 1000 by 1000 pixel, right, rather than using all 1000, probably you can use only 100 and still achieve the approximate image. And you'll better understand this image compression when we discuss about SVD.